Okay, I think we can start. Today we have Pau Luque, who is doing the PhD here at Media, and he's going to talk about the challenging aspect of monitoring coastal dynamics. And yeah, it's fun.
Thank you, Dave. And thank you for being here and for people who is organizing this, because in the end, having this place presenting is quite important. Now, from a PhD perspective, I even see it more important. And also, I'd like to thank Julia, because she gave me her space today so I can present. So thank you. But I'm going to start with this. So most of you know, as Tim said, that I'm doing coastal research from a physical perspective. But I think that only some of you remember my last presentation, because it was in San Sebastián last year, so 6 people on the room. But well, the good thing is that as this presentation, that one was recorded, as all of them, and actually I've seen many of them on YouTube afterwards, so I recommend to see them. Actually, that's why I said that they do a really good job here. So I actually recommend seeing all of them, but specifically, I don't recommend watching mine. You see, since I did the presentation last year, the work changed significantly. So instead, and now it starts my advertisement space, I recommend you to read our paper, which was published around 6 months after the presentation, which has the updated knowledge, let's say. And so if you don't want to read all that stuff with differential equations, which I wouldn't read either, but it's quite interesting, so you have to overcome this barrier. If some of you happen to be at New Orleans later on this month, you can also come to our presentation Tuesday at 9:20 in the Asian Science meeting. So that's another option. And here ends my advertisement space. So to begin with the presentation, as you may imagine about this kind of research, well, actually, it's a problem, I think, which is common in all research, no? That we need data continuously, validating our models, getting ideas or insight to prepare our theories, just to, I mean, without data, we cannot do anything. And here is no difference. So now pretend this is a beach, okay? The sea, here you have the sloping part of the beach, let's say sandy beach, and then the Viking promenade, or whatever you have behind the beach, okay? So just to have an example to give you in place, that's the kind of measurements we need. The sea level, the shoreline position, and you can relate that to the presentation I gave last time. Because this is basically the relation between these two is what we studied last year, and also like all the topography, you know, the map of elevations of the whole beach, the wave state. That's basically the most important variables we used to deal with. And so to get that information, we have different strategies. The classical one, oops, I don't want to poke this person head. So the classical one was the in-situ measurement. Okay, here we have an example. Let's say a moored instrument like a buoy or any other stuff, and then just instrumentation. You can measure transects in the beach, just moving with the GPS or with some kind of theodolite. You can measure the depth of the submerged part of the beach with a boat. And now we don't have to use this cable sound. We have now sonar with echo sounder. So this is the classical stuff. The problem is you have to go there, like all your time is going there. Actually, we have people here in the Balearic Islands, mostly from Sosiphu and Italy, who do this stuff, and actually very grateful about this, because otherwise it would be the whole day there. So, and then this kind of instruments, you know, electronics and water are not very good friends. Electronics and salty water are even worse friends. So we would like, although this is constantly used, and it's used as a ground truth because the best measurements we can have, we would like to have, and we try to have other kind of platforms to do the measurement. And basically we do this just by taking out the instruments and taking the measurements from another place. Basically, we do remote observation of these variables from outside the beach. The instruments can be placed in different platforms, can be earthborne, if we just place them behind the beach, or can be airborne, or even spaceborne. You see, here I try to depict a plane and a drone, although it does not seem so. You see planes were used extensively in the past, but now we have a very rise of the use of drones because they don't need a pilot in there. They're cheaper, so you can just get your drone piloted and get information from different sites. Although airborne platforms offer the best opportunity because you can just put an instrument, let's say a camera or another instrument, I would say, in a few moments and just measure continuously what you have on the beach. With this, you have to pilot them somehow, even you are on the aircraft or not. So they give you the opportunity to be in different places, but it doesn't give you that many high values of sampling frequency in time. And then spaceborne instruments and platforms, satellites basically, you see, you can get to very remote study sites, and you also basically get information, let's say, for free, because putting a satellite in orbit is very difficult, managing the data is very difficult, but as a user, just downloading it and using it, you don't have to go to the place to take the measurements, so that's nice. So it's very important, or very useful for, you see, for sites which are very far away from remote places, or just as opportunistic extra information stream of measurements to complement with this. But I'm going to focus with airborne platforms because it's what we do here at the research group, and also because, as I said, this offers the maximum sampling frequency about all the remote sensing platforms. Also, what I think they have in common is that in here you can just span a small space of your, let's say, study domain, because either you have to move through all of it, so you spend a lot of time, or you just can place some instruments, so you only can cover parts of the space. Although with these kind of platforms, you can just expand all these areas. So in general, these remote sensing alternatives have higher sampling frequency and higher space coverage. And now to see what we have in here, now in the Balearic Islands, we have 3 coastal sites actively monitored from this physical perspective, and it's very short-lived. And the kind of instruments we have, there are these biannual campaigns to get information in planes. And very thankful for all of the people who does this at the group monitoring facility, because we can do this kind of information, and airborne platform with video cameras, regular video cameras right now. And well, the thing is that we are in touch with these people who manage these study sites, and we want to try to improve the conditions of these kind of instruments by adding new ones. So you see, the most important problem of the video cameras, so now I'm only going to talk about airborne platforms. There are so many main problems. The first one is that we need specific illumination conditions. You see, you can have 2 types of instruments, passive ones, which basically are cameras and receive radiation from the sun, so you can get the information, or active ones, so you send some kind of energy and get back the information, such as radars, sonars, or even lidars, depending on which kind of let's say, wave do you send to the measurement. So the thing is that cameras, you see, they need good illumination conditions. So basically it means that they are half the time useless. During the night, they cannot measure at all. And also this kind of situation, which we think is very nice to go to the beach to see a sunset, no use at all. If you have this glare from the sun in the images when the sun rises, the sun is setting, and also if you have different illumination conditions, a cloud passes by and then goes away again, it just messes up all the information you can get from the sensor. And actually, we have worked and we have some publications about how to mitigate this effect with cameras. But again, when we have no light at all, it's no use. So now in our current project, In-situ Coast, we have the idea of using, exploring what we can do in one of these measurement sites and adding new type of instruments to overcome these problems. So I'm going to start with the other problem regular cameras have. You can see the whole picture. The other problem cameras have is that in the set of variables we want to measure, remember the examples I gave you before, they cannot have information about wave height or sea level. You see, with the one camera, you just get the picture. You can see how it evolves through time. You can see the shoreline because you have a nice picture of it, but you don't have depth information. But if you combine two of them, and that's one of the proposals we have for this project at In-situ Coast, get multiple cameras in a stereoscopic configuration, you can get depth information from the images, and then you can use it to reconstruct the sea surface. And actually, it has been done. This is from a platform in deep sea, and the cameras are really near to the sea surface, but it can be done. And actually, having some seminal experiments in beaches, although were successful, but now we have more options. The other instrument we want to add is a radar, because you see radar is sending electromagnetic radiation, but it's one of these kind of active instruments, so it can work at night. It can work at any illumination conditions, and so it's the perfect ally to complement all the information we're currently getting for the cameras. And that's what we're going to talk about from now on. Just as I mentioned, we are also planning to build and place under the sea, anchored at the bed, some kind of cheap pressure and sonar sensor, so we can get in-situ measurements from here. And since you see the problem in beaches, you have very hard conditions. It's not only salty water, as I said before. You see, you have a storm and a wave is anchored at 10 meters depth, is even 20 meters depth, I don't know, whatever. You see in there, you have the wave, but you don't have anything below at the seabed. At 1 meter depth, the very shallow waters, you place something, you have strong currents, so you just get wiped out everything what you put. So putting cheap sensors is nice because you can just replace them. So we have the idea just to complement all the information and also help to validate the information we get from this, and hopefully get a whole picture, continuous picture and of all variables and through time and space of what we want to measure, so we can go back to studying the coastal system. So from now on, I'm only going to talk about radar. You see, as I said, it works just by this is the radar, and this is target, in this case the sea, but let's say any target from now. And what we do is we send a pulse of electromagnetic radiation, and we just get a reflection from the object, and we measure it at the radar again. So from the perspective of the instrument, you have the pulse that you send it, and then another pulse. And since the speed of light is known, you just need to measure how much time does the radiation needs to go back, just to guess what is the distance to the object. And that way, in this way, you can just, by sending pulses of electromagnetic waves, know how far are the targets. In this case, this can be used to know, you see, get a map of the elevation in the sea. This is a very bit more complex, the effects it occurs, but the basic principles are this. So you basically have a map of the elevation at your side, and so you can get more information. The thing is, actually, you're not sending just a signal like I have 5 volts and then I have nothing. You see, you have a modulated signal. It means that it's actually a very fast signal. The radars are used for studying beaches about 10 gigahertz. So the thing is that the pulse you get back is just of the same frequency that the one that you sent. But if the target is moving, happens with waves, you just get by the Doppler effect, you get a pulse of different frequency that you send it. If the object is moving towards the radar, you get faster oscillating electromagnetic wave, and if it's going away, it's the other way around. So these are pulsed radars, and these have been used for coastal research about 20 years on this moment. And you see, the problem they have is they need very high powers, the order of 10 kilowatts, and this is a bit difficult to get. Also, they are switching continuously to get this electromagnetic radiation on and off, and you need a very complex electronics to get this. Very short pulses, and this means that you need a very fast electronics to switch all this power on and off, and also to record the time you have your targets. So this means that these kind of radars are quite expensive, and also can be, up to this point, dangerous to operate, because you see you have very high power, very high tensions, and constantly switching on and off of electronic components. So an alternative is continuous wave radar. In a continuous wave radar, instead of switching on and off and sending a pulse, we're constantly sending information, electromagnetic radiation to the target. But you see, then the problem is that you don't have any pulse you can measure back, because you're constantly sending electromagnetic radiation. So what we could measure the speed of the target by these Doppler measurements pulse radars have, but we can do it better. Actually, if instead of sending a signal of constant frequency, we start to modulate to send an electromagnetic radiation, which is with upper and high frequency, we start changing this frequency of the radiation we are sending. You see what happens. And this, instead of being a plot of the amplitude of the signal we are sending, this is a plot of the frequency we are sending, and in blue the frequency we're getting back. Since the radiation takes a time to go and come back from your target, in this case the seed, when you measure the frequency of the signal you get back, it will be different of the frequency you are sending in that specific moment. And so with this difference, you are able to know how much time has passed. And so how far away is your target? So this is continuous wave radars. The good thing about this is that they need quite smaller power to operate, and you don't need as much faster electronics, and the generator is always running. So these are cheaper, easier to operate, and actually it hasn't been much explored in the literature in this field, and are going to be used in a lot of fields now. So, as I said, just by getting the frequency of the signal you are receiving, you can get the distances of all the targets you have, in this case from all the parts of the sea, just by measuring the frequencies of the signals you get. At the same time, if you are doing different measurements in time, and your targets are moving, you see you get the same signal back, but a bit out of phase. And so you can compare the phases of the signals you get back, and this way you can also get, as you have with pulsed radars, the distance of the targets and the speed of the targets. So basically, this all means that you are able to, with cheaper and safer electronics, get the amplitude and get the speed of the sea surface at the coastal locations in this case. So as I said, there are very few examples of the literature with the use of continuous wave radars. With pulsed radars, you have tens and tens of articles, but with these kinds of radars, you only have 3 of them. One from 2006, when they just placed the radar just in front of the shoreline and get some measurements of the very close section, and they demonstrated this can be done. And then from experiments quite recent, one from Canada, when they put the radar just in front in a boat again, and measuring only a small piece of the sea surface they have in front. And this article that just came out some months ago, where the researchers put the continuous wave radar here. I don't know if you can see this properly from there, but this is basically Napoli, and you here have this peak. I don't know how it's called in English. Like, okay, like makes sense. So the radar here, and again they measure just in the cross section. So thank you. The thing is, with these examples, we can say, as I told you, that both the powers required to operate the radar and the times are more easy to go by. And so what we propose is to use this, and so I told you that we are sending a signal is going up and down frequency. What we propose is the following. So we are sending different realization. Actually, we are doing now 1 each second, and in each second we're just doing different ramps of frequency. So with each ramp of frequency, we're able to get different measures, which we can just use to compute the distance of the sea in this case. And from consecutive measurements, we are able to get the speed, as I told you before. So the thing is that if you're doing this each second, you basically have the amplitude and the speed of the sea surface sampled at each second. So you can get this through time and get this information to get the spectral information of the sea. So basically, you can have the frequencies of the waves you are having at the moment. And this is one example that this can be done. This was measured by our collaborator, Alberta Huasca in Barcelona some months ago, and I processed the data. The thing is, basically, we are having this radar placed at 40 meters height and about 100 meters from the sea. So it was not that much close as the example. So this can be done also at the distance. And we measured, as I just explained it, the sea surface in a transect to start with. And so after this processing, we are able to get this kind of spectrum. This is normalized, just not to bother about this. And so here we have a section of the zone of interest between 200 and 300 meters, which is completely onto the sea surface. And here you have the range of spectrum we have. So basically the red lines, because we are doing this, as I said, for every point in this transect. So in all the points measured, the spectrum is varying between these two lines. These are the 75 and 95. This is the median, and this is the mean of the spectrum. So basically, we're able to get the spectral content of waves. And actually, these dots are the measurements that you can take from the peak of the spectrum and the mean value of the spectrum by this measurement with continuous wave X-band radar. And these blue and black lines are the ones reported by the boy in Barcelona, which was quite close by when measurements were made. So you see that here you have this location mark as the maximum of the spectrum, but you see as the we don't have the whole spectral data, which is something we are waiting for now. It can be that the spectrum has been saved here because it just coincides with other peaks. So we are now hoping to get this data soon, and we can validate that actually we can have the whole spectrum of waves at the sea just by measuring with radar at this far away, which has already been done until this point. And well, that was all because that was work in progress, but it can be done. So thank you for your attention. Yes.
So that was very interesting. I wonder whether you can expand a little bit on how and what is the effect of Doppler shift on the measurements that you made. You said that you measure the phase shift, but actually, in theory, right, you're going to get a frequency shift because of Doppler. So how would you then distinguish between an object being at a different distance but being fixed from being at another distance?
Yes.
Such a way that when it moves, it gives you the equivalent shift.
Yeah, actually, you cannot separate this information.
Oh.
The thing is, if you have this radar, actually, instead of having 1 point, you will have 4 points, because you don't know exactly if the shape of the Doppler, or if the frequency done to the distance. The thing is that you see the frequency that you get to get the distance. This is the frequency you have from this shift here of the signal you send, are actually quite more sensitive than the Doppler shift of the velocities we are measuring. So it depends. You cannot measure very fast targets with this, but the speeds that we are having, the surface currents, the speed of the waves, the effect they have, the shift they have on this, because actually they shift, they have a shift, is not comparable with the one you're having here. So the thing is that with this part of here, you can actually distinguish quite good only the distance, and then you get this kind of interferometry. You see the changing phase of the signal you get, because just a slight movement of the target, we are talking about 10 gigahertz in this case. They were even 77 gigahertz. So the wavelengths are so small that even a slight movement causes a big phase shift. So actually, the phase measurement is quite good to measure the speed here, because it's very sensitive to the speeds of the targets, as well as the other measurement with the continuous wave radar of the measuring the frequency of the signal you get by is very sensitive to the distance of the target.
But you're combining measurements from different directions, right?
Not in this case. In this case, we're only measuring in one transect. Actually, you have to move the radar. So you can get static radar, but you need a lot of antennas just to do like moving the radar, but electronically, let's say. So the thing that's important, you only get the speed relative to the radar, not the whole speed. So you only get one component, the velocity of wave. Yes.
So compared to the X-band radar,
Yes.
I mean, what you said before, that it's cheaper and safer, but then if you get an X-band radar and get a transect from that, would it be like similar than the information you get?
Yes, you actually can do it. In fact, with X-band radars, you only don't do transect, you actually move the antenna continuously, so you get whole pictures, but we're still testing this, so we haven't still started to move it yet.
But you will get the...
But yeah, you can get the same information. So the way you get the information is different, and actually we can see how it compares between the actual pulsed X-band radars and the continuous wave X-band radars. But the thing is that you can do it with a cheaper instrument, which is safer to operate. So basically this, I mean, we only wanted to use a radar, in this case X-band, because it's the one that goes well for this kind of environments and measurements. And the thing was, well, to select the radar, we have this dichotomy, we know that this works, so that we'll be just applying them, and these different kind of radars which haven't used that matching here, so you can get the same information, and the thing was to validate that actually you can do it, because you have that validation just for very close measurements, and knowing very well the ambient you're wearing by. So the thing is that, yes, you can get the same. Actually, this is all to get the same with the other kind of radars. Yes. Yes?
Do you think it's possible to measure the way setup with this radar?
I don't think so. You see, the problem with the radar is that you get the distance from the radar to the target, in this case, the sea surface. So you actually you are not getting the, how to see it. So you're measuring whole transect at the same time. You don't have the opportunity. Imagine this is the beach, right? And this is the sea. You are not measuring like this, so you're getting in every point. You're measuring by transects. And so the radar is the one to tell you at which distance you have it. So it's amplitude and speed. The thing is that if you have a wave setup, it means that the sea surface is closer to you, to the radar in this case, near the shoreline. So when you have this information, you don't know if this distance is due to the wave setup or is due to you are measuring a point near you. So you don't have this kind of information. Actually, the radar tells you the distance, and you assume this is the distance to a flat. See? So the radar is not very well suited for this. You could use it using a very directive antenna, but these are more difficult to operate. Instead, I would rely on a LiDAR because you can get a really small footprint, and you see the same that you are doing with the radar, which is sending electromagnetic radiation, but with the LiDAR you're sending electromagnetic radiation which is basically light. You see this kind of frequency, and this can be get a very small footprint. So this means that now you can make a transect measuring the different points, so you can see at each angle at which distance you have the sea surface. So now you can reconstruct at which distance in the horizontal you have your sea surface. So this could be a way, but with the radar you cannot, because you have to distinguish the distance of the whole line just by the information. So you have this both variables mixed. You know if the distance to the target is due to the horizontal distance or to the elevation of the buoy setup.
And when you say that you have compared the spectrum with a buoy,
Yes.
how much the depth of buoy was?
Well, the buoy is at the entrance, not at the entrance, a bit far away from the port of Barcelona, so it's not inside.
I know.
But so it could change the amplitude of the spectrum, but the periods we not expect it to change it that much, just slightly, if any case. So this can be used to the spectrum of the periods of the spectrum to get the amplitude. They depend on the depth. That's why we want the whole spectrum, and knowing the depth, we can try to convert somehow and compare them.
But you can theoretically compare with the significant wave height, right? If you reconstruct the spectrum, can you do that?
Yes, not yet, because the problem we have is that we are having only the how to tell it, the integrated statistical parameters, like period. In period, you can also with significant wave height, but in this case, what we want to know is first if we can reconstruct the frequency spectrum of the waves, and then if we can adjust, because you see the signal you get from the radar is not directly the wave amplitude or the wave height. You have to go in between them, and we don't want to still try to make this adjustment until we get a clean spectrum, because if we do reconstruction with a bad spectrum, then you don't want to get a good measurement in this case. But yeah, that's the final objective. Yes.
Would it be complex, maybe with an array of radar, to have an idea of the spatial scales involved? Because I think you are focusing in the temporal scales that maybe are the more interesting one. But what about the spatial scales of the waves? Are they of interest or possible to estimate?
Yes, they actually have a lot of interest because we use them to infer depth. So with video cameras, one of the applications they have, you get both the frequency and the wavelength of the wave speed, which are equivalent of the waves, and so you can use that information point-wisely to reconstruct the depth from there. With radar, you can also do that. If you do a whole picture of the sea in one transect, you can to make some approximations. There are other ways, but again, you need to have the correction of the amplitude to amplitude. To radar amplitude, signal amplitude to wave amplitude. That's it. To do it. But yes, completely, they are of interest because they have this information about all the variables we want to measure. And also it's important, I didn't say it, but you need, when you have the radar, you need to have a footprint. This means the surface that gets illuminated when you send the radiation, you need it to be small enough so you can capture a fraction of the wave. So imagine you have, let's say, one whole period of wave or 2 or 3 wavelengths of waves, and you illuminated them, and you try to extract some information. You just get an average flat one. So you get both the information about the smaller footprint and then capacity to get it.
And related to this, are you already tried to combine maybe the information from the image with the information from the radar?
Not yet. That's actually that is the really final step, which is to combine to do a fusion with the different measurement sources, because they all have advantages and disadvantages. So good thing is that, for example, you can use radar to keep the approximation of the variable during the night, and then go back with camera during the day, which now are more developed to get all this information. Because now you have your estimate, and during night it deteriorates. So having some kind of estimate that you can do, for example, in a Kalman filter, that you need some kind of estimation prior to the measurement. So radars can provide this. Also, many different ways to do it, but of course. So the thing is to complement measures to get a better estimate, and to make the same measurement with different platforms to get a more close estimation of the variable. Both of the are the objectives of the project. Okay.
More questions? Yep. Thank you, Pau.
Thank you.